All right, in 6.2, we're going to look at one-to-one functions and their inverses. And, a one-to-one function is just basically is a function where no y values are repeated. So to be a function itself, you cannot repeat x values. So one-to-one just means they are y values and no y values are repeated. So we're going to determine that from a graph only. And we're going to use what's called the horizontal line test. And basically, if a horizontal line intersects a graph one time, the function is one-to-one because that shows us that y values are not repeated. So for this first example here, you can see no matter how many times we draw a line through these graphs here, it only intersects it one time. So this one we can consider one-to-one. This one here is not. It's a parabola. It's from an x squared graph. And even though it is a function, a line intersects it twice. So it is not one-to-one. And the reason why we just need to know this is because in this section, when we're doing inverses, we're only going to be dealing with functions that are one-to-one. So sometimes you will see in your homework restrictions on domains, and that's to make a one-to-one function. Because this parabola here is not one-to-one, but if I only showed you half of it, it would be one-to-one. So therefore, if I only choose x's bigger than or equal to 0, I would only have half of it, which would make it one-to-one. So if you do notice that on your domains, that's what it's for. The next item we want to talk about is the inverse functions. There are three ways to find an inverse. You can find an inverse from points, you can find it from a graph, or you can find it from an equation. So you'll see that we have notation for inverse, and it's that -1 exponent. That just indicates the inverse of the function f that you start with. So let's first look at inverse from points. To find an inverse when given a point, we reverse the coordinates. So if this is the set of points we're given here, f inverse would be 3, 2, 4, -1, and -8, 5. So to find the inverse from points, you just reverse and interchange x and y. So that's how to find it from points. The next item is how to find the inverse from a graph. Well, think about how we found inverse from points. We just reverse the coordinates. So if I have a section of a graph here, and if I look at the f itself, these points are -3, 0, 0, 2, and 1, 2. So the inverse, we would reverse the coordinates. Now we plot them. So we've got 0, -3. We've got 2, 0, and we've got 2, 1. And we draw it, and that would be the inverse of this. Now, one way to always kind of tell that your inverse is correct is it should be symmetrical about this line, y equals x. So as you can see, these points are all equidistant from this line, which means that this is the line of symmetry. So that's one way you can always check to see if your inverse is correct when you're graphing it. Now, we can also find the inverse from a graph once we make the graph. So here the graph was given to us. So let's look at one where we're not given the graph. So we want to graph the original function. And then just find the inverse using the points. Check to make sure the graph is symmetrical. So let's say, for example, I have f of x is 2x minus 3. Well, I'm just going to find 2 points because it is a straight line. And the two easiest x's normally are 0 and 1. So if x is 0, I get negative 3 because 2 times 0 is 0 minus 3 is negative 3. If x is 1, I get negative 1. So I plot 0, negative 3, 1, negative 1. And I draw it. Now I don't even need the equation to graph the inverse. So f inverse of x, all I'm going to do is reverse the coordinates. So I just got negative 3, 0, negative 1, 1. Plot them. And draw it. And as you can see, when we check about that line y equals x, it is symmetrical. Okay? So, they don't always have to intersect. I mean, most of the time they will within the confines of your graph, but they don't always do it. But you can just kind of tell, especially if you use graph paper, it's much easier to tell if your inverse is correct. Okay, so that's, finding the inverse from points and from a graph. They're very much the same thing because you need points to make a graph. The third way we're going to do it is finding an inverse from an equation. There are steps involved. Now, let me just do a few examples. If I have just a basic function of 2x, the inverse of 2x is x divided by 2 because you're doing the opposite operation. So the inverse of x plus 2 would be x minus 2. The inverse of x squared would be the square root of x. So keep that in mind that, inverse does not mean opposite signs. Many people get confused and they just think it's changing everything from positive to negative or vice versa. You're actually doing the opposite operations. Now, we'll do some more of these in class, but I'm going to give you the steps here on how to do it. But if you look at this equation before I go through the steps, think about the opposite of 3x minus 2. Well, the opposite of 3x minus 2 would be if I added 2 and divided by 3, because you always reverse the operations to get the inverse. You always do the opposite of addition or subtraction first and then do division. So a lot of times you can get the inverse without going through these steps here. But I'm going to show you how we got to this by doing the steps. And the reason why we do these steps is to get an equation we can solve for. So what we do is we first change f of x to y. Step 2, we interchange x and y. That means we just reverse the x and y, and that kind of gets us back to reversing the coordinates. We're just interchanging x and y. And then the third thing is we go ahead and solve for y. So I'm just flip-flopping my equations here. And now I'm going to solve for y. So what I do to solve for y is I add 2 to both sides. Divide both sides by 3. And so this is how I get to here, is by solving. And then I just go ahead and say f inverse of x is x plus 2 over 3. Okay, so before we work this one, go ahead and give it a shot. See what you think the inverse is. Try to figure it out without going through the steps. See if you get it right. So I'll give you 10 seconds. That's all you need. All right, let's go ahead and see if you're right. It's going to be one of the two. The inverse is either going to be the square root of x plus 5 or the square root of x plus 5. So it's one of the two. So let's follow the steps. Step 1, I'm going to interchange x and y. Rewrite, change f of x to y. Step 2, I'm going to now interchange x and y. I'm not interchanging x squared and y. I'm just interchanging the x and the y. Now I'm going to solve for y. So I'm going to go ahead and flip-flop my sides. I'm going to add 5 to both sides. And then to get y by itself, I've got to do the square root of both sides. So the inverse was our second choice up top here. And again, the reason why it's not this first choice is because I have to add 5, then take the square root. So always think about reversing your operations and always get rid of addition and subtraction first. Okay? So these are, it's a topic that some people do struggle with. So just try to follow the steps. Don't worry about why it works. Just follow the steps. Now, the last thing we're going to look at in the inverse section is we're going to verify that two functions are inverses. So how we can test that we're right, that 3x plus 1 and x minus 1 over 3 are inverses, is we can do their compositions. We can do f of g and g of f. If they both work out to equal x, then we know they're inverses. So if I'm going to show that f of x and g of x are inverses, I'm going to find the composition of f of g of x, which is f of x minus 1 over 3. So I substitute. And I simplify. So the 3's cancel. Minus 1 plus 1 cancel. And I end up with x. Now I'm going to do g of f of x. G of f of x is g of 3x plus 1. So I go ahead and substitute this 3x plus 1 in for this x here. And remember, you always simplify in grouping symbols before you do anything else. 3's cancel, and I'm left with x. Okay? So that is your verification that two functions are inverses. It's more compositions like we did in 6.1. All right, so that's 6.2, our inverses. Now we're going to move on to 6.3. And 6.3, we're going to be introduced to exponential functions. You've got to know how to use your calculator. And we will do more of these in class, more practice using our calculator, just to make sure you understand how to do exponential functions. But what you'll notice about an exponential function is the x is the exponent, and that's why we call them exponential. Pretty bright. Genius, actually, to call an exponential function because x is in the exponent. I'm just kidding. So, if I have this function here, 2 to the x, and if I want to find f of 2, I put 2 in the exponent, square it, and get 4. F of negative 2 is 2 to the negative 2 power, and it's going to give you 0.25. And if you forgot why that works, your rules of exponents, when the exponent's negative, to make it positive, we write the reciprocal. We then get the fraction 1/4, and we can make it a decimal. Okay, so, if I want to do 3 to the x, f of 2 is 3 squared, which is 9. And I think most of us are okay with these. It's when we get into B, C, and D. We've got a fraction as an exponent here. We got pi as an exponent here. Then we got the square root of 2. So, if I want to do negative 2/3, what I have is 3 raised to the negative 2/3 power. To get the answer correct here, you have got to make sure that you know how to put this exponent into your calculator. So depending on what kind of calculator you have, you might have this button right here, which is raised to the power, and then you've got to put negative 2 divided by 3 inside parentheses. So, as I am working with you, make sure you're working with me. And what you should get for this is 0.48. Now, again, we will work more of these in class, but, try this out and make sure you know how to do it. If you have a calculator like the one I'm using at home here, it doesn't have the exponent button, but it has a y to the x button. So what I do is I do 3 y to the x, parentheses, 2 divided by 3, negative parentheses equals, and I'll get it. So there's lots of different ways, depending on your calculator, to get these. You just have to know how to do it, okay? The next one, f of pi, well, most of your calculators have pi, either as a button on its own or in one of the second functions. So if I want to do 3 raised to the pi, in this calculator, I would do 3 y to the x pi equals, and I get 31.54. Now, the last one there, the square root of 2, is a little harder, simply because, how do we enter all this into our calculator, especially with one of these? It makes it very difficult because you got to use grouping symbols, all kinds of things. But what you always have an option to do is you can always find the square root of 2, make it a decimal. So if I do 2 square root, I get 1.41. So I can simply go ahead and find the exponent as a decimal and do my 3 y to the x, 1.41, and I get about 4.71, okay? So again, we'll do more practice on this in class. Bring your calculators, especially bring your calculators from here on out. I know most of you bring them every day anyway, but if you don't, make sure you bring them. Your phones, they're not the greatest calculators in the world, but if you know how to work it, that's fine. Especially once we start doing other functions. All right. Next thing we're going to look at are the graphs of the exponential functions. So your graph of the exponential function always has a curve of some sort in it. The reason why is because functions grow exponentially. They grow very quickly. This graph here is the graph of an exponential function when my base, which is a, don't forget a is your base, x is your exponent, is bigger than 1. So therefore it's like, 1.5, 2, 3, 4, whatever. It's bigger than 1. So it's going to grow very rapidly. We've got a horizontal asymptote here of y equals 0. It never crosses the x-axis as it's just a base to the exponent. We have our y-intercept. And you always have a y-intercept with an exponential function. Sometimes you will have an x-intercept, but not always. In this one, we do not have one. Now, we look at a different graph here. It still has a curve, and as x gets bigger, y gets really, really small, but never approaches 0. And this is where your base is like a fraction. So this could be something like this. 1/2 to the x power. So anytime you have a fractional base, your exponential is going to look like this. Again, it still has the horizontal asymptote and still has the y-intercept. So we're going to look at graphing these by shifting up, down, right, left. Okay? So it's kind of like what we did in section 3.5. So vertical shifts are going to look like plus a number or minus a number. It's not in the exponent. So they're just going to be up and down. A horizontal shift is where your subtraction or your addition is in the exponent. And it's still like we did last section in 3.5. It's opposite the sign. So let's look at first a graph with a horizontal shift. So remember, 3 to the x, a is bigger than 1. It's going to look like this. And we're going to shift f of x is 3 to the x, right, 1 unit. Well, the easiest thing to move is the y-intercept. And then you just sketch it. It's not going to cross over the x-axis. We can find the y-intercept by letting x be 0, but we're just doing shifts, so we don't have to worry about it. So the best way to do it is to shift the y-intercept. The horizontal asymptote remains the same as y equals 0. And so you're done. Okay? So that's a horizontal shift. This next example is first of all a vertical shift. And since it's a fractional base, it's going to look like this. So again, we're going to shift f of x is 1/3 to the x down 1 unit. So I just move the y-intercept down. I shift the horizontal asymptote down 1. And I just, whoops, almost messed up here. I just sketch it. Okay, so make sure when you draw these, it does not cross over your horizontal asymptote. Okay? So that's your exponential function to where you have the base is some number either bigger than 1 or between 0 and 1. Your base will always be positive, so we don't need to worry about negatives. And that's how you graph them. Now, this next item on our agenda is the natural exponential function. We have a letter E on our calculator. And on this calculator here, my E is above this LN button. Right there is my E to the X. Your calculator should probably be the same. You should have a natural logarithm with the natural exponential as its inverse, and the common logarithm, which we'll get to down the road, which has 10 to the X as its inverse. So, if I wanted to see what it actually was, it's 2.71828. It's kind of like pi. Okay? It's an irrational number. That's what it stands for. But it's one of those numbers that comes up a lot in formulas. So they gave it its own button on the calculator. And we can evaluate these as well. So if I wanted to do E cubed, now on this calculator here, I have to enter the exponent first, so it depends upon your calculator you're using. So in this one, I would press 3 second to access the e to the x function, and I get 20.09 if I round. The next one here is interesting. If you have a calculator like mine, it's probably easier to do this in 2 steps. So if you have a calculator where you can just type everything in as you go, then just type 2e to the x and type in your exponent and hit equals. What I've got to do, makes it easier for me, is I'm going to do 0.53 negative second e to the x, and I get 0.589. Then I take that times 2, and I get roughly 1.18. So, you just got to get comfortable using your calculator and know how to use it. Okay. The last one, e to the 4.8 power for this calculator here. I got to do 4.8 second e, and I get 121.51. Okay, so, you got to know how to use your calculator, especially in this section. So do lots of practice, bring it, and we'll do more of these in class. And that way you can get some good practice with me helping you. And we can also graph the natural exponential function. Since e is bigger than 1, it's going to look just like the other exponential function. It's going to have that curve to it. It's going to have the y-intercept, the horizontal asymptote. Has it all. And we're going to graph it the same way we did earlier, paying attention to whether it's a vertical or a horizontal shift. So in this case, this is a vertical shift. So to graph this, I'm going to shift this down 2 units. So again, move the y-intercept and your horizontal asymptote down 2, and then just sketch it. Okay, so we'll do lots of practice. We got 2 sections to cover in class. So again, bring your calculator, and we'll see you in class.